Yes, you may. The path is hanging. So f of x is equal to x cubed minus 7x minus 6 all over x squared minus 9. And this is period 4, August 30th, AP Calc, looking at page 81. Yeah, it's a sad 3. I apologize. It's a sad looking 3. Okay. All right, so this would be called, this is a rational function, so let's go ahead and write that. This is a rational function. This is a rational function. It still isn't making me, I'm not totally happy. It's almost like a 9. So make that look a lot more clear. Okay? So if we were to factor the denominator, it says, what is the domain of f? That's correct. Good. Good. So. No. It only is what it is. Nothing more. Okay, here's another thing I guys want to tell you guys. Calculus, in a lot of ways, to me, is easier than pre-calculus because it's very linear. You learn about the derivative. You learn to take the derivative of various functions. You do that, you learn some different tricks like product rule and chain rule and all that. And then you look at anti-differentiation, also known as integration, and you do some of those problems, and that's calculus. That's AP Calc 1. Or Calc 1 and the college level, AP Calc, all the same thing. It's not, I don't want you guys to be intimidated. Because I know, again, from what I learned from your background from yesterday with my conversation.
We did all of that. We just don't know pre-calc.
Yeah, we just
I don't know how to do that.
So the pre-calc is missing with the idea of limits, which is very important, especially when taking the AP Calc exam. So I want you guys to know that if you stick with it, you will do well. I think it's not as intimidating as some people make it out to be. So let's go ahead and factor the denominator. We have x plus 3 times x minus 3. So yes, the domain.
What is it?
We could say all reals except plus or minus 3.
Can we get back to the question again?
Hello. What's your name?
Oh, we did this to you?
At the end of class, let's go ahead and turn those forms into me, and we'll do that.
What about 10?
Yeah, this is the problem that I initially had an issue with, is like this whole thing here. So they're here, they're going down there. I'm going to leave that with her. Okay, thank you.
If we get back to the question on the closure and S, do you want us to write that, or do you want us to write it in like the parentheses?
Don't stick it on the TV. You probably should be familiar with both. I'm fine with you writing it like this. But you should also be familiar with, let's make sure we know this. You guys should also see it as this. You go, okay, the domain is, say, interval notation. You say from negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. You guys ever seen this before?
Yeah.
Interval notation? Okay. You should be familiar with that.
Oh my gosh. I never learned that.
I think I've done it before, but I don't think I've
Interval notation? Yeah. Because it can be all reals except plus or minus 3. So if you imagine going all the way from negative infinity up to negative 3, and it's important that it's in a parentheses because it doesn't include, right? Bracket includes the value.
Wait, so why is there not a bracket around, like, infinity and negative?
Because infinity and negative, they're not numbers. It's just an idea of going on forever in that direction. They're not actually values that you can contain. Yes. That's number 2. Yep. Number 2, investigate the graph of f around x equals 3 to see that f has a removable discontinuity at x equals 3.
So does that mean it won't be at x equals 3?
Okay.
So you have to factor the top 2, right?
So number 2, investigate the graph of f around x equals 3 to see that f has a removable discontinuity at x equals 3. So it's already told me it's removable. So in factored form, let's go. I'm going to go to the next page. Okay. Okay. I'm going to go to the next page, and we have.
So you just factor the top and show that.
Yeah. So that tells me something. That tells me that according to number 2, and I'll do that in a different color, so it's not. This number 2 is step 2. Okay. According to this, it tells me that it's removable. So I know algebraically off the bat that the top, I am able to factor out this from the numerator. And this guy here is still... Okay, so now what will this guy be here? This again might be something you never covered because of the situation that happened last year. Sorry, go ahead.
I'm sorry. Okay.
Okay, so if I factor out x minus 3, let's see, I have x cubed minus 7x minus 6. Let's see this. So I'm doing this. Minus 7x. Have you guys ever done long division before?
Oh yeah,
Yeah, that's fine.
Okay, we can do that.
Well, wait, I have a question now.
Yes.
Before you do any of this, the only reason that you knew that the top had an x minus 3 is because the book told you, right?
Yep.
So if you didn't have that and it was telling you to like graph it,
Mm-hmm.
you wouldn't be able to do that.
Would we still factor it and then see that?
But you wouldn't know that there's a hole.
You would.
Oh, then we
Because the reason is because the graph would look incredibly different because it'd be a vertical asymptote and you have this going on.
I know, but
and
I'm
this
saying
going
when you're factoring the top, you don't know there's a hole yet.
Yeah.
So how well, yeah, but he's factoring it by assuming already that there's a hole. By knowing that
Because-
the top has an x
Be-
minus 3, and
That's
that's how
because
it's
the
factoring.
graph would show me that there is, because the graph would show me that there's not a vertical asymptote.
But I thought you didn't see it. I thought you were trying to graph it.
Nope.
Oh.
I'm not trying to graph
So
it.
you see a graph already?
Nope.
No, we know that.
We know
Let me
there's
get you a
hole.
textbook.
It says it's
But you don't want a textbook.
discontinuity.
Okay.
It's
So
discontinuity.
all it says is number 2 is investigate the graph of f around x equals 3 to see that f has a removable discontinuity. So I punch in my graphing calculator and I
So
see
it tells
that.
you already that it has a removable discontinuity.
Yes, it tells you that.
Yep.
Okay, so that's what I was
So if I looked at the graph, I could see, even if this didn't tell me number 2, if I graphed this on the graphing calculator, I'd see, oh, there's no vertical asymptote at x equals 3, so there definitely is a hole, which means that this occurred. It was a removable discontinuity.
Oh, I see.
Okay? So, but what?
So that's why you're doing the long division?
Yeah, you can do long or synthetic. You could technically synthetic because it's a linear factor, yeah. You could do
Oh,
synthetic.
we've done synthetic too. But I don't.
I don't care what method you use. So here we any other questions before I do it? Okay. So x squared, we get what? X cubed minus 3x squared. I'm gonna subtract this whole thing. You guys remember doing these? Yeah. So you have 3x squared minus 7x minus 6. You have plus 3x, you get 3x squared minus 9x, and subtract this guy here, and you would get 2x minus 6, and then plus 2, and 2x minus 6, so there is no remainder, so the other factor would be x squared plus 3x plus 2.
print that by multiplying it, so.
Yep.
So,
So then the x minus 3 is cancel out, so if you're gonna write like the final equation.
Yeah, so of course this is why it's called a removal discontinuity, because now we can see here and here simplifying to 1 and 1, leaving you x squared plus 3x plus 2 all over x plus 3.
Would there be an asymptote?
Good. Yes, there would be. Yeah. So let's write the emphasis when we're talking about this. So there's definitely a hole at x equals 3, and there is a vertical asymptote at x equals negative 3.
What is that number?
Why is there no asymptote?
okay, so okay.
Is that all?
What's that at?
So let's specify that here, so we're all good. So this is a different color. So this is a hole is a removable discontinuity, and this is a non-removable discontinuity.
So I understand.
The whole is, because it told us the whole is at x equals 3. How do we know the vertical asymptote is negative 3?
Because this x plus 3 does not simplify with another factor that is exactly x plus 3.
Okay, so whatever is left on the denominator when dealing with these removable stuff is our vertical asymptote.
Yeah, exactly. Or there can be more than one. Yeah.
Okay, cool.
Yeah. Very good.
Wait. The vertical asymptote is at negative 3, but isn't that removable?
No,
The x
it's not
minus
removable
3.
because the linear factor is x plus 3,
When you solve it?
and so it doesn't.
Wait, why did you have to do long
X minus 3 when you solve it turns into
Now, make sure. Let's say you didn't know anything and you have
Oh
to
my
keep going
gosh.
on. You could factor
You have to
this
solve it.
further,
Figure out what the other factors.
but you're going to find out one of the factors is not x plus 3.
But how do you, wait, how
That
do
just
you know
makes
how
so
to
much
use,
more sense.
x minus and use the factor line how to choose? It told us. Was that just because the book? Yeah, because they gave you that.
If the book tells you, but also, yeah, if you graphed it, you would see, oh, there's no vertical asymptote at what I would have expected if it was non-removable, but because there is no vertical asymptote, it definitely removed.
So if you didn't have the given, you just graph it and then figure it out from there?
What do you mean didn't have? Do you mean what they say for number 2?
Right.
Yeah, exactly. You graph it and you'd see, oh, there's no vertical asymptote at x equals 3, so there was a removable discontinuity.
So a function is.
I would have been a little nervous if this wasn't like on the OPRO. I'd say put it that way. It's got to be no remainder. What's
When
that?
is a function, just go over again, when is a function discontinuous and when is it continuous?
So a function is continuous is if I can take my finger and trace it all the way from negative infinity to infinity, and I never have to lift my finger.
Okay,
That
so
makes
it's
sense.
discontinuous when there's a hole or.
You see that's really far?
Or these ones. Oh, when they go.
There's a break.
They go all the way to infinity.
Wait, what did you say?
It's discontinuous if there's a hole in it, or like these ones.
Or if there's an asymptote. Yeah. If you do like this.
Let's go back to this
I
guy.
just wanted like.
Perfect example.
See, there's a hole.
If I trace my finger here, I have to lift my finger off, jump all the way down to here. No, I know it looks, I'm not trying to be funny. And then to continue moving right, I have to lift my finger at this exact point in time, jump infinitely close to the right of this hole, and then continue. So this is discontinuous. I know this kills you for some reason. I don't know, I'm not
understand why the
sure.
line doesn't go down.
What? I don't know what you're
You're just telling me that there is a point right there. There's just a point right there. Like,
What?
that's
When
it.
it's part of the function, not on the
It doesn't have to be
line.
connected. It
Wait,
doesn't have to be.
Then it's not part of the function.
Yes, it is.
okay,
And you will
just-
have a
how is
problem.
that part of the, wait, like,
That
how do I
is
get
what it
there?
is.
How do I get there?
Okay, we don't have to talk about it. But just the basic principle. All right, what, yes. You were asking something, too. Yes? There is hope. There is hope. Yes, hopefully. Go ahead. I'm sorry. I know that's, I'm sorry. Go ahead. What's that?
It's not, it's a discontinuous.
Oh, yeah, vertical asymptote, yeah. Yeah. Now that itself, you would go on forever, and actually you would never actually get to the other part theoretically. But yeah, it's definitely discontinuity. Yeah.
It's gonna be one of those things we forget and never study right before the test.
No, guys, this is easy. Discontinuity is easy. If I have to lift my finger, it's discontinuous.
It doesn't continue.
Okay. I have to answer this if it's my what I think it is.
It's like a movie, the whole ride and movie, the whole
Also, when you if there's a horizontal asymptote, is that
What's the question?
I'm
sorry, I can't hear you. I can't hear Hope, guys.
Asymptote is horizontal. Is it discontinuous?
Not necessarily.
Because it's still going
I will show you examples.
Wait, I'm confused.
Hold on, one thing at a time. One thing at a time. Hope asked if there is a horizontal asymptote, does that mean that it's discontinuous? And the answer is not necessarily. So let's say the horizontal asymptote is the x-axis, okay? And this is your function. This is not discontinuous.
Oh,
It goes from negative to
never
positive. If it's going this way, then it doesn't ever, you know.
But if
Like,
it's
if
like,
it-
Right, does that make sense?
You could easily go this way, but like if it was vertical, you couldn't.
Yeah, I'd have to lift my finger. Well, I'd never get there. I'd just be. I would never get to the other part of the
With the
function.
vertical, that's when.
So there's definitely a break. There's definitely a break. Yes.
Continue.
The big word that we're learning right now, does it only have to do with the x-axis?
Discontinuity.
Yeah, that
I
thing.
do know that.
So we're
It only have to do. All I'm talking about is if a function is discontinuous, meaning it has a break at somewhere. It has a break. I have to lift my finger off at some point.
What?
Does that answer your question? If I have to lift my finger, it's
So
discontinuous.
if there's a point where it's undefined on the function, that's considered a discontinuous. I was trying to, like, I understand the whole, like, if there's a break in it, but, so if there's something.
Because undefined is going to be a hole or an asymptote.
Okay.
Yeah.
Wouldn't that still be discontinuous, because it looks like there's another asymptote, like a vertical?
I did not mean to imply that it looks like that. I'm sorry. Did not mean to imply that. Here, we'll make it. There.
I just want to make sure.
Good question.
There
Good
are
question.
graphs
Yes,
like that
that's a
that
good
don't
question.
have that.
Good question. Good point. Okay. You good? All right.
I have another question
Yes.
about this problem. So I graphed it on the question.
Okay, so we go back up. I'm good. So let me go back to there. That is. Bless you. Bless you. Yes.
So I graphed it, right?
Mhm.
And it looks like this.
Mhm.
And the asymptote is at x minus 3. How can there be a hole?
No,
No.
that's stopping
then
you
what
now.
is it? Okay, then what
The
am I asking?
asymptote looks at the x equals -3. You're getting linear factors confused with the x is.
Wait, you have to
If
solve
I
that.
substitute
That's
3
supposed to
into
solve
this
something.
guy to make it 0, not this guy. The solution, but the x equals 3, I'm referring to this guy here, not this guy.
I know. What I'm asking is,
Yes.
if it never touches x minus 3, how can there?
Never touches, that makes no sense what you're saying. Then if
Like
it's
it
x
never
minus
touches,
3.
like where x equals -3.
Okay,
It never.
that makes sense.
It never. If it never.
There is no
Yeah,
point, there is no
exactly.
point at x
If it
equals 3,
never
that's correct.
gets there, like if that's where the asymptote is, then how? So because I know you can't here, you can't see the removable point, but there would be a removable point at x equals +3.
Absolutely,
Okay. So that's okay. Then never mind. I figured it out.
Oh,
So this is the idea here.
Yeah.
Okay, so let's move on. Everyone good? You may use the restroom.
I have to find that where we're saying, where Hannah is actually grammatically correct, because it's like the second, I'll find it and show you.
Yeah,
You really
please.
gotta go with.
Number 3.
with your time.
Okay. How should f be defined at x equals 3 to remove the discontinuity? Use zoom in and tables as necessary.
What is any of that?
Okay, guys, okay,
It can
so,
be undefined.
No.
okay. So if you look ahead, you can just jump to the piecewise function underneath number 5, and this is how you end up defining it. Because you're going to find out that what the value would have been 10/3 if you made it continuous. Yeah.
Apparently we should have learned that, but I think I saw it. I think I saw it for like 2 seconds.
If you didn't factor, wouldn't it not have a discount?
I'm sorry, I can't hear you. What?
If you didn't factor the original, wouldn't it not have a discontinuity because?
That's throwing me out. The way you're asking, wouldn't it not? It's killing me. I'm sorry, I can't understand. Yeah, it's too much. It's still morning.
Barely.
If you didn't factor the function, would it be considered continuous?
Whether you factor or not, this graph will look the exact same whether you factor or not. Factoring just lets you see things. Yes.
What exactly is it asking? It's asking us to.
What number? 3? Where we
Yes.
are? Okay, thank you. What it's saying is, if this hole didn't exist, what would its y value be? And they're saying, use your calculator, you can zoom in the hole and see what you'd see.
Would you just plug in 3 for the equation?
Sorry, 2 things at once. What?
Would you just plug in 3 for the equation?
If you plug in 3, it won't work.
So yeah, if you plug in 3 into the original, it won't work. But if you plug in 3 after you remove these guys, it'll give you what they're talking about. So the whole purpose of this problem, for those of you that have a book in front of you on page 81, to go from the given and to rewrite it as the piecewise function g of x, so that you're removing the discontinuity. All you're doing is filling in that hole. That's all this is demonstrating.
But I thought there was nothing in the hole, so how can we?
Because we're changing it, we're making a different
If there
function.
was,
We're creating a different function. So let's say we wanted to make it continuous. Then we would have to write this guy as g of x is underneath number 5.
How do you do that? How do you do that?
Well, you simplify this and you would plug in 3 and see what the value would be. So it should end up being 10/3.
So you're basically graphing the function without the discontinuity.
Not even graphing, but just writing the algebra
Like when you, okay. Yeah.
Yes, you may.
So you would write it.
I've already demonstrated 4, by the way. Yes.
It would be, wouldn't it be just f of x squared plus 3x plus 2 over x plus 3, plug x into that, because that's what you have left when you cancel out the x minus 3. Okay, that's a lot. Yeah.
I'm not quite sure if I picked up everything on that. Sorry.
When you're trying to, okay, because that's not really what I'm seeing here. I don't understand how that relates to what it's.
They rewrote this function as a different function, g of x. G of x will look exactly like f of x. For those of you that are looking on page 81, g of x will look just like f of x, except that hole will be filled in. That's it.
Wait, what's the bottom of it?
The 10/3,
Yeah.
that's saying that g of x, the value of the function g of x is 10/3 when x is 3.
So 3 and 5. Oh, okay.
You're doing the same one for 3 and 5.
Yeah, that's exactly why I shot from number 3 to look at the one that you would come up with for underneath 5, yeah. 4 I've already demonstrated using long division, so there's no remainder when I factored out x minus 3. And so then 5 actually shows the extended function. And it's just extended because you made up another part, the 10/3 when x is 3. That's why. So therefore, you've made it continuous around that point, x equals 3. That's all. It's all that this is. If you guys understand that we're just filling in that point, that's pretty much all this is. The main point to understand from this is that the value of that hole, if it was filled in, would be 10/3. That's kind of the main one. But it's also good, you've got your algebra skills to know how to factor, your review of long division. It's good stuff to know.
Just looking at this.
Yeah, if the wording is really
Yeah, the wording is really confusing.
Yeah.
Okay? What can you be more specific?
Well, no, like the wordings for the questions, like it looks intimidating. Like show that x minus 3 is a factor of the numerator of f and remove all common factors. Like
Okay.
I feel like they could have just said do long division, and then like I get
Okay.
do long division.
So it's
like, just
so Do you know what factor means?
Well, yeah, like I get it, I just have to look closely at it, like first
Okay.
time glancing at it, I'm like, wait, what? And then I'm like, oh, that's what they're asking.
So you do understand it? Okay.
It's just, I feel like they could have put it in simpler terms, but I understand.
Okay. This is a more advanced math textbook. This is typically a college level course, so that's why they're doing that.
I get it.
Yeah. Hopefully, I'll be the guy that breaks it. That's kind of part of my job, I guess, is to break it down so it's easier to understand. There's properties, continuous functions. It's common sense stuff. I'm not going to test you on Theorem 6. I'm not going to test you on specifically on Theorem 7. This is stuff that is kind of like what you're saying there, Jessica, where they make it more complicated than it is. It feels like, so Theorem 6, Theorem 7, common sense. Theorem 8, common sense. I'm not going to focus on those things. Okay. What I think would be good to do would I'll give you guys the option. We can move on to section 2.4 where we start discussing rates of change and tangent lines, or we can, we'll do a vote by hands, or review the algebra, basically the stuff you should kind of have an idea, the review sheet that I gave you, and continue with those problems.
No, let's do 2.4.
Okay, 2.4, good choice. 2.4, rates of change and tangent lines. So, this is what differential calculus is all about, is rates of change. Now we're getting closer to the derivative. Okay. So some of you may have done this, but realize that there are other people in this class that may have not come the same background as you. So I'm definitely going to go over components that I think are absolutely relevant to the course. Anyone have any questions on average rate of change? Please raise your hand. Average rate of change if you don't understand average rate of change. What was that?
Can we just do like
Did
one?
you say something? Okay, yes.
Can we just do like one problem? Like,
Sure.
Going over 2.4.
Sure.
It's basically like what a derivative is.
No, she's asking because I was just going to skip over it. So she's asking a legitimate question. So yeah, we
Yeah, I
can
just
do
want
it.
to do like one.
So if you look at page 87, you have f of 1 equals 0, f of 3 equals 24. Find the average rate of change over the interval from 1 to 3, inclusive of 1 and 3. So you just the endpoints. So I wonder if they have the same example. You know what's a better example is where they have a graph. So on page 87, you can actually see the points 23, 150, and the other point Q, 45, 340. All this is slope, as you guys know it. So up to this point, how familiar are you guys with slope? Okay.
I
Okay.
never actually learned slope.
But I know it. I never actually learned it though.
Okay. And they give some examples, just average rate of change,
We in Cambridge for sure.
basically rise and run. And this is what's called the secant line. So the secant line is drawn between 2 points on a function. That is the secant line. So let's get some terminology here. So let's see here. So secant line. This is a line drawn that it touches a function at 2 points. And its slope provides average rate of change.
Can it be between any 2 points of a function?
Yep, that would be called secant line, yep. Of course, your average rate of change is going to vary depending on which 2 points you pick, of course.
That's why.
That's the secant line. And then we have the tangent line. Let's not talk about food, please.
Sandwich there, Mr. Nick. Sorry.
Some student asked me about sandwich at the beginning of last class, and I got my peanut butter and jelly spiel, and I don't know where it came from. So it came from another class.
Yeah, you asked how do I do this, how do I do that, so.
Peanut butter and jelly?
Like how you make a sandwich.
Okay, this is being recorded, it's important. You gotta go to Publix and you gotta get the real peanut butter. You can look at the ingredients, it's just peanuts and salt. No sugar, none of that extra nonsense, you don't need that, okay? Yes.
She's passionate.
How do you make peanut butter?
They
How
take,
does
what they do,
don't have
Grind peanuts.
You have to put butter.
They just grind peanuts.
She puts butter on her.
Now, that's a good question, because if it's not just peanuts and salt, they're lying to me, because the ingredients are just peanuts and salt, so.
If you just grind.
I think there's a natural oil,
Yeah, there is.
and that's why you get that oil out of it that rises to the
Yeah,
top,
that's why.
which scares a lot of people that don't
I really
understand
believe in
food.
butter.
Natural oil.
Yeah, but what do you do?
Right, oh yeah,
You're
you
doing
got-
sandwiches. You didn't finish. What-
You
what
got,
do you
okay,
do?
so you
Do
gotta
add
get,
peanut butter?
I'm not going too fancy here, but the peanut butter, once you have the real stuff, you just don't go back.
Are you a vegan or a vegetarian?
No, neither.
Let it finish. I want to finish. That's all right. I'm curious.
So, you gotta get, it doesn't matter crunchy or creamy, crunchy just gets in the way.
Yeah.
Just go creamy. And the crunchy's only gonna last like the first 4 scoops, and then you have no more of the crunchy. So, go with the creamy. Publix brand, peanuts and salt. There's no extra stuff, okay? You do that, then you go and you get whatever jam you like, okay? I like with the seeds because it tastes real to me, but I can suffer and go with the jelly, okay? You gotta do that, and then I'll do like the Nature's Own butter bread, and I'm good to go. And I only do whole milk. None of this 1%, 2% nonsense. Get out of here. Whole milk, I want the real deal.
Thank you.
Whole milk, organic, nowhere to go. I'm making a bonus question. You know the answer, you don't want to write it, you want the bonus. Touches a function at, yes?
Have you ever been to Devil Hours?
I've heard such good things about them.
My dad loves their peanut butter, that's all he eats now.
You buy the raw milk from That's so good.
Does anyone know? The phones, please, except mine, because I have an emergency. Okay, touches a function at one point, and its slope provides, calculus. Its slope provides and it's a good question, the instantaneous, oh, that's a big word, especially for me, instantaneous rate of change.
I hate that concept. I hate
You
it.
hate what concept? Then you hate calculus. I'm sorry you hate calculus. Hopefully I'll get to the point to where you don't hate it. And hopefully in the very future, because we're about to go
If you
into
can make that make sense.
next class, probably the derivative looks like. So its slope provides instantaneous rate of change.
You're gonna have to talk about all of that one topic.
Of
Rate
the-
of change at one point.
And I understand if some of you don't get it,
Yeah, the tangent is like a thermometer.
Yeah.
so secant line, tangent line. So this is something the secant line, the slope of the secant line provide average change that the Greeks understood for a long time. But for the longest time, they couldn't understand instantaneous rate of change, and they thought that motion may have actually been an illusion. It wasn't until not Einstein, the guy, one of the inventors of calculus, you have Leibniz and you have Newton. Isaac Newton came along about 350 years ago, and this concept of the slope of the tangent line provides instantaneous rate of change. And we'll get into the mathematics of it, we only have like 4 minutes, so probably not this class. Yes?
When do you need to know, or like when do you need to
The best answer is the best answer. That's what like a mathematician's answer would be that's a silly question. Because that would be the mathematician, because they just do math like from a pure math standpoint.
They just do it to do
if
it.
it comes up with something that's true, it's true. But a more practical, everyday man's answer as to what's the point of finding the slope of a tangent line is because you could
tell me the instantaneous velocity of, let's say, anything.
So yeah, so when you had it, that was explained this.
So, but like,
At that point in time.
that's my job. Okay, so that's the question that we have. At this point, what is the rate of change?
Well, you might pull up a few questions.
What was the second part?
Like after you use that.
I only heard the first part. I don't want to. Did you get it? The first part I heard was correct. Yeah, it's like the question asks, what is the instantaneous rate of change of the function at this point? You would know intuitively that that's the slope of the tangent line. And next class, hopefully I'll demonstrate that you'll know that you're finding the derivative at that point.
I want to be a professional grapher who specializes in thinking and stuff.
No, they're always like actually really cool jobs.
I'm gonna stop.